So now that we've looked a little bit at how equilibrium is established and what happens at equilibrium, is there any way that we can change equilibrium? And so what we mean by that is, what we mean by that can be demonstrated. So we've already looked at equilibrium, how equilibrium is established, what happens at equilibrium, all of that. But is there any way that we can change where equilibrium lies? And we can demonstrate what we mean by that by considering the conversion of NO2 into N2O4 that we saw earlier. So we saw this information. Initially, before equilibrium was established, we had no N2O4 and we had 2 moles per liter concentration of NO2. And then at equilibrium, we saw that we formed 0.14 moles per liter concentration of N2O4 and then a concentration of 1.72 for NO2. Now that's great and all, but why can't I get more N2O4 and less NO2? What happens if I want to get more of a product or less of a product? Or I just want to get rid of some of my reactants. Well, some guy named Henry Le Chatelier came up with a brilliant solution to this, which was that equilibriums are very finicky. Equilibriums exist at certain concentrations, they exist at certain temperatures, and they exist at certain pressures. And by changing any of those 3 variables, by increasing the temperature, increasing the pressure, or increasing the concentration of some species, I can change where equilibrium likes to sit. An amazing example of Le Chatelier's principle would be the Haber-Bosch process, which is just about creating ammonia from N2 and a couple of other molecules. But it's actually one other molecule, but it's one of the favorite topics for exam writers. And so if you go and you just watch a YouTube video or 2 about the Haber-Bosch process, you can probably find out a lot of good information and how it relates to Le Chatelier's principle. But so Le Chatelier's principle, a system currently at equilibrium can be influenced to a different equilibrium if a stress is placed on said system. So because these equilibriums are so finicky, they are sitting at a low stress point. And if I put some kind of stress on it, that system is going to try to figure out a way to limit the stress on the overall system. So if my reaction has a certain concentration of a certain molecule, I can give more of that molecule in, and the system's going to say, oh, we have too much of that, let's use some of it and make some more of the product or reactant. So what that all means is 3 ways to change it. Let's see what happens when we change any of those 3 variables. So the first one is pressure. And so for pressure, what happens if we increase it? Well, let's just say we're talking about a balloon here. And I know that inside of a balloon are a bunch of gaseous molecules that are bouncing off the side of the wall, creating a pressure inside of that space. Now, that pressure at equilibrium is where the pressure likes to lie. So what happens if I increase the pressure on that system? The system is going to try to figure out a way to get rid of that pressure. And the most popular way that a system can figure out how to do that is by looking and saying, all right, well, gaseous molecules cause pressure. So if I want to lower the pressure because there's too much of it right now, I can try to lower the amount of molecules that are causing the pressure. And so in this case, if I have an equilibrium where I have 2 reactants forming 1 product, well, there are more molecules on this side than there are this side. So if I have an increase of pressure, and I'm trying to now decrease pressure to limit that stress, I'm going to convert more of my A and B reactants into products. So what's the effect? My equilibrium will move to the right. I'll now favor having more of my products as a result of the increase of pressure. Now, on the flip side, what happens if I decrease pressure? Well, if I decrease pressure, now I'm going to try to increase the pressure to make up for that decrease. So how is that going to happen? Well, I'm going to take my C's, turn them back into A's and B's, therefore increasing the amount of molecules and therefore increasing the pressure. So here, I will be taking my my products, turning them into reactants, so my equilibrium will move to the left. So that is pressure, and pressure is probably the most complicated one. But as long as you think of it in terms of, oh, if someone tries to increase the pressure on me, I'm going to try to decrease the pressure through any means necessary. What happens if I change the concentration? Well, let's say I have the same exact reaction, A plus B becomes C. It's at equilibrium, the rates are the same. And I increase the amount of A. Well, think of it in terms of this. So let's say that I know at equilibrium there is a certain balance of my reactants. My reactants don't change concentration, neither do my products. And I know it's not always, like we're shown here, a 1-to-1, but it's going to help for this example. We know that the numbers don't change, but they stay at this constant rate. But they change, you get what I'm saying. So if I suddenly increase the concentration of one of the reactants or products, in this case the reactants, what's going to happen? Well, I'm going to throw off my equilibrium. Now I'm going to have too much of one of the molecules, not enough of the other. So my reaction is going to say, oh, well, let's shift equilibrium this way. Let's form more of these green molecules and get rid of some of these blue molecules as a result. And doing so, I will now reform equilibrium. So originally here I had 4 greens, 4 blues. Now I have 8 blues, 4 greens. Now I have 6 blues and 6 greens. So too much of one molecule, get rid of it. Make more of the other molecules. If I need to get rid of some molecules, I'm just going to get rid of them by using them to form the products. So adding reactants, I'll now make more products to get rid of those reactants. So equilibrium moves to the right. How about in the next case? Removing reactants. Well, if you get rid of my reactants, I'll make more of them. So if I now decrease A or B, well, I'll be throwing balance off, so more C's will be used to form A and B. So equilibrium will shift to the left. Look at me saving 2 seconds. If I add products, well, too many products, I'll get rid of them. by using them to form more A's and B's. Again, equilibrium will shift to the left. And lastly, for concentration, removing products. Well, if I lose some of my products, I'll just remake more of them, reform balance. So I will cause the equilibrium to move to the right. And that's two of the major ways that we can change the equilibrium. Now let's look at temperature. So, as it turns out, one of the reactions we talked about briefly is the NO2 conversion into N2O4 and heat. It turns out that when I actually make N2O4 from NO2, I release heat. Heat's a product. And so if I think of heat as a product, I can just treat it like a normal product. So in this case, the fact that I am releasing energy, I'm releasing energy when I convert NO2 into N2O4 means there is thermal energy going out. So exo, moving outwards, thermo, heat escaping is exothermic. So what happens to this system if I add heat? Well, I'm just going to treat it like another reactant. So if I now have an increase in heat, I'm going to try to get rid of that heat. And how am I going to get rid of that heat? Well, if I release energy by doing this reaction as read from left to right, I can use energy using it in the equation as read from right to left. So I'm going to shift equilibrium to the left for an exothermic reaction. So I'm just going to keep copying these. Equilibrium moves to the left, just so I can get rid of some of that excess heat. What else we got? What if we remove heat? Well, if I lose heat, I'm going to want to reform it. I'll do the forward reaction more to produce more heat, and then we'll have the equilibrium moving to the right. How about endothermic? Well, now we need to add heat in the forward reaction. So if we need to add heat to do a reaction, what happens if we keep on adding more and more heat? Well, I want to use that heat. So this equilibrium will now move to the right to get rid of all this extra heat that I'm using, or that I have. So equilibrium will move to the right. And lastly, let's see, exothermic, endothermic, adding heat, taking away heat from an endothermic reaction. So now we've got less heat. So if the reaction of C becoming A and B produces heat, and I'm now too cold, let's produce some heat. Let's use some of C, and we'll get the equilibrium to shift to the left. Great. Now let's check our concept knowledge. So in the following reaction, increasing the pressure would, well, if I increase the pressure, I'm going to want to get rid of some of our molecules. Molecules exert pressure. If I have too much pressure now, get rid of the molecules that are exerting pressure. So, increasing the pressure, there's 4 molecules on this side, there's 2 on this side. So, I'm going to want to get rid of some of these C's and D's and reform A and B. So, what's going to happen? D and C go down, A and B go up, cause D to decrease, looks good to me, cause no change, not according to La Chatelier, needs more information on your life, cause A to decrease, we're causing it to increase, so it is A. In the following reaction, adding a catalyst for the forward reaction would, what do you think? Catalysts do a lot of amazing things, but here's an important thing, and we're going to write this big. Catalysts do not affect equilibrium. I'm writing it huge, but trust me, it deserves to be written huge. Catalysts, no effect on equilibrium. They do not have any impact on equilibrium. Remember that. That just gets all of the test makers hot and bothered when they think about asking that question. Remember that. No effect on K equilibrium, on the equilibrium constant. No change. All right, we've stressed that enough. In the following exothermic reaction, adding heat would, oh boy, now we're just told it's exothermic. Well, if we're told it's exothermic, that means that this reaction, as written this way, A plus B producing 3 C's, also releases heat. So I'm just going to write as a product plus heat. So adding heat would do what? Well, if I increase the heat, I'm going to want to get rid of that heat. The reaction of 3 C's becoming an A plus B is going to require heat. So if my temperature is too high, I can lower the temperature by using this heat. So if I'm using 3C plus heat, I'm going to be dropping my amount of C, increasing A and B. There is literally no D. I'm not decreasing A. I definitely will have an impact on KEQ. Ooh, no effect or increase KEQ. Well, that's more interesting. I could literally just do process of elimination right now, but I know that KEQ, as written, is 3C, or sorry, go. C to the power of 3 over A and B. So if I'm now using more of my C, I'm going to have a lower amount of C. I'm going to have a higher amount of A and B. Fascinating. Guess what? The answer should be, you know what, let's just leave it there, and we'll just write E. Decrease KEQ. Even better, by the time you see this, this very silly answer choice will now say decrease KEQ. And pick that one. That one's going to be the good one.